Assalamualaikum warahmatullahi wabarakatuh, and good day everyone. Okay, today's lecture I'm going to cover chapter 4 in our syllabus, which is spectroscopic method of analysis, and chapter 5, 6, 7 and 8 you will learn about all the instrument. Okay, now we look at the first slide, the definition of the spectroscopy. So, spectroscopy is the study of the interaction between the matter and the electromagnetic radiation as a function of the wavelength or the frequency of the radiation. So, historically, the spectroscopy originated as the study of the wavelength dependence of the absorption by gas phase matter of visible light dispersed by a prism. So the basic principle set by all spectroscopy techniques, for example UV visible spectroscopy, is to shine a beam or of electromagnetic radiation onto a sample, and we observe how it responds to such a stimulus. And the response is usually recorded as a function of radiation wavelength. And a plot of the response as a function of wavelength, or more commonly frequency, is referred to as a spectrum. As we can see, we have 1, 2, 3, 4, 5, 6, 7 color of visible spectrum, and each color have its own wavelength, which is indicate from 4 times 10 to the power of -7 to 7 times 10 to the power of -7. And the one at the left is high energy, and the most right contains low energy in wavelength. So spectroscopy is the study of the interaction of electromagnetic radiation and the matter. So what is actually electromagnetic radiation? So it is any form of radiant energy that is propagated as wave and include what we commonly call visible light. Electromagnetic radiation is characterized by the wave properties of frequency, wavelength, and also the velocity. So all electromagnetic radiation travel in a vacuum at a constant velocity, which is the speed of light. So this light carries energy in the form of tiny particles known as photon. Light has wave property with characteristic wavelength and frequency, and the range of wavelength and frequency in light is known as the electromagnetic spectrum. So this one is the electromagnetic spectrum. The entire range of wavelength of the electromagnetic radiation, we call it as the electromagnetic spectrum, as shown in this figure. We have on the most left side, we have a radio wave, microwave, infrared, UV, X-rays, and gamma rays. Okay, the gamma rays produce a very high energy. So the electromagnetic spectrum is made up of many different kinds of radiation, from low frequency, low energy radio wave with long wavelength to high frequency, which high energy gamma rays with short wavelength. Okay, so high energy will produce short wavelength. This experiment target the visible region of this spectrum specifically because we can see the electromagnetic radiation with wavelength in this region with our own eyes, right? So the speed of light move at 3 times 10 to the power of 8 m/s in vacuum meter over second. And the wave number is 1 over wavelength, and the frequency in gigahertz, which is 1 hertz, equal to 1 over second. And spectra are observed when matter emits or absorbs light. When an object acts as a source of radiation, so it is said to emit radiation. When radiation from another source interacts with matter, the matter is said to absorb radiation. Alright, so this is some figure about the UV visible spectroscopy principle. Spectrometry is the measurement of the plot response as a function of wavelength and an instrument which performs such measurement. Okay, this is the principle of UVVs. Okay, although we see the sunlight or the white light here um, as uniform or homogeneous in color, it is actually composed of a broad range of radiation wavelength in the ultraviolet, visible, and also the infrared portion of the spectrum. So it contains actually the 7 color, and as shown on the figure, the component color of the visible portion can be separated by passing the sunlight or the white light through a prism. Okay, this one is the prism, which it acts to bend the light in differing degrees according to the wavelength. And electromagnetic radiation, such as the visible light, is commonly treated as a wave phenomenon characterized by wavelength or frequency, as I mentioned earlier. And the light will then pass through this separated, and we call it as the incident light with a single light, and then transmitted through the solution, which is absorbed by the solution and will be detected as a reading or the graph that should be appeared at the detector. In UVVs, the prism we call it as the monochromator, and the wavelength selector, or also called as slit, is used to produce the incident light to the sample solution in the cuvette. Right, the square is a cuvette. We call it as a cuvette, the place where we put our solution in. In our solution, which is our compound to be analyzed, it contains molecule atoms that vibrates when it absorbs the light. And then the reading of the molecule is by it absorbs which wavelength, which is indicated by the color figure that will display on the graph. For example, if the absorption of 420 to 430 nanometer light, it will render a substance of yellow color, and absorption of 500 to 520 light make it red. And green is unique in that it can be created by absorption close to 400 nanometer as well as absorption near 800 nanometer. So earlier, human valued colored pigment and used them for decorative purpose, as we all use the chromatography method to analyze the color directly. But this one is a very advanced material, very advanced instrument for you to determine the wavelength of the compound. Right, now we look at how does light interact with matter. So light can interact in 3 ways. First one is by reflected, which is light wave bound of objects. The second one, light is absorbed, which is light is taken in object. And the third one is transmitted, which is light passes through matter. For example, light is absorbed. We can see in the slide. For example, feeling the heat of the glass. If you touch a glass that is heat or on place on heat, so you can feel that the glass is absorb the heat, so you can feel the hot of the glass. Okay, light is reflected. For example, seeing your reflection in glass. Reflection or reflected is when the light bounce off an object. So if the surface is smooth and shiny, like glass, water, or the polished metal, the light will reflect at the same angle as it hit the surface. And transmitted, for example, seen through the glass, whereby when light travels through a medium such as glass without being reflected, absorbed, or scattered. So when this happens, light energy is not lost and can be considered 100% transmitted. So optical surfaces are coated with various material to reduce reflection losses. For example, you use your glasses to wear. Okay, so it is transmitted. Okay, now we look at the formula. For light wave, the frequency and the wavelength are inversely related, and their product is equal to the velocity, which is given by v equal to c over lambda. And frequency is generally measured in hertz cycle per second, right? Then 1/second. So wavelength can be measured in any units for length, but nanometers, which is 1 nanometer equal to 1 times 10 to the power of -9 meter, and meters are common. So the energy E of the electromagnetic radiation is directly proportional to its frequency, which is the E is for energy, equal to H times with V. H is the Planck constant, which is equal to 6.626 times 10 to the power of -34 joule per second per photon. So thus, given any one of the three parameters, the frequency, wavelength, or the energy, the other two can be calculated. So based on the relationship, high energy radiation E will have high frequency and short wavelength, and vice versa. What happens when light interacts with matter? First, we look at the region of spectrum in radio frequency and the energy transition in radio frequency. The atom will nuclear spin and electronic spin. In microwave, when light interact with matter in microwave, the atom will rotate at its place. For infrared, the atom will vibrate. In UV visible, the atom will move in electronic motion, and X-rays, the bond will breaking. In nuclear magnetic resonance NMR spectroscopy, the radiation is radio wave, which is in the range of 10 to the power to the -3 meter. An electron will flipping the magnetic spins. So electron will spin when it interact, the matter interact with the light. For infrared spectroscopy, which is FTIR, the infrared radiation is in the range of from 10 to the power of -5 meter, and the molecule will vibrate when it interact with light. In UV visible spectroscopy, the ultraviolet is 10 to the power of -8 meter, and we can see that the electron promoted to higher level energy. It has its electronic motion and electronic energy band. So in UVVs, we can see that the energy have its level, which is once the electron is in the excited state, the higher energy level, it is in a more unstable position than it was when it was in its relaxed, or we call it as a ground state. Alright, so common types of spectroscopy. We have fluorescent spectroscopy, X-ray, flame spectroscopy, plasma, sparks. So we will cover about UVV spectroscopy, infrared spectroscopy only in this syllabus PST 351. So again, what is light? Light is a form of energy known as electromagnetic radiation. So in spectroscopy, we use light, right? So light carries energy in the form of tiny particles known as photon. And light has wave properties which characteristic wavelength and frequency. Light travels as an electromagnetic wave, and light travels through the vacuum of space, unlike sound. It travels at 300 km per second. So a car would take 177 years if according to the light travel, but light only takes 8 minutes. Electromagnetic radiation is a form of energy, sometimes called radiant energy or optical energy. So properties of electromagnetic radiation, they are all propagating or moving form of energy. They all travel at a velocity which is the speed of light, and they all having wave-like characteristic, and the most familiar is visible light.